So in the last class, we sort of discussed the operation of a fiber optic directional coupler and how it can be used to split the power into two different channels in whatever ratio we want. Right? So this directional coupler can be used for other applications also. So today let's look at one which is a wavelength division multiplexer. Also, sometimes known as a WDM coupler. WDM stands for wavelength division multiplexing. So as the name suggests, basically, so for various applications, we want to sometimes combine or separate signals on two different wavelengths, right? Either we want to combine signals coming at two different wavelengths into one fiber, or we want to split them into two different paths, right? So one can use this directional coupler device to do that. So recall, so there were two input ports, 1 and 2, right? Output ports, and there was this coupling region here of some length L. Right, so last time we saw, for example, if you send some power in port 1, depending on the parameters here, some fraction of the power comes out here and the other remaining fraction comes out here, and that was for a particular wavelength, right? So sometimes, for example, let's say we have some signal here, so there are two different wavelengths traveling to this and coming to this fiber, and we want to split these two wavelengths into two different paths, right? So let's say they're carrying different data that we want to send to different places. So basically we want, so for example, lambda 1 to come out of this port and lambda 2 to come out of this port. Right, so recall that the coupling coefficient here depended on wavelength, right? So it depended on some overlap integral, and so it depended on the mode profile, and also it had a factor of wavelength directly coming in, right? So basically the different wavelengths will have different coupling coefficients here for a given like separation between the cores. And if we design the parameters correctly, then we can basically design this coupler to do this functionality, right? So basically to do that, what we want is, so at the output, right? So in port 2, right, we want, so the power in port 2 at wavelength lambda 1, we want this to be 0, right? Basically we want lambda 1 to come out only of port 1. And recall, so the power in port 2 went something as, so the input power, so that would be the power in port 1 at lambda 1 input. Right? So that's the power coming in from here at lambda 1. Right, so kappa 1 would be the coupling coefficient at the wavelength lambda 1, right? And the power coupled to the other port goes as sine square of kappa times L, we saw that last time. Right, so we want this to be 0 for lambda 1, right? So from here you can see that, so at lambda 1, the coupling coefficient times the length should be some integer multiple of pi. Right, so some positive integer here. And now for lambda 2, right, we want it to come out of port 2 only. So if you look at the power coming out of port 2 at the wavelength lambda 2, that we want to be equal to the input power from here at lambda 2. Right, so again this equate. So now the power here will be sine square kappa 2 of times L. So kappa 2 is the coupling coefficient at lambda 2. Right, so from here, so we want sine kappa L to be 1 now instead of 0. So kappa 2 times L, right, so then it's some half integer times pi. Right? So last time we saw that how we could calculate or estimate these coupling coefficients, right? Given some V number and distance between the cores and parameters of the fiber here, right? So let's say we, for some application, we want to separate some wavelengths, then basically use those design parameters, we can find out what lengths we need and what should be the separation of the core of the coupler here to do this functionality for that particular wavelength, right? So for example, so consider a coupler here with identical fibers. So both 1 and 2 fibers are identical. So this is the phase matched case. So let's say the fibers have standard single mode fiber parameters. Okay, so core and cladding index is around 1.45, and then core radius about 5.5 micron. Right, so let's say the two wavelengths that we want to separate are so let's say lambda 1 is 1.55 micron. So for these parameters, the V number at this wavelength would be 1.9. Okay. Let's say the other wavelength is 1.3 micron. So these two are important wavelengths, as you know, in optical communication, right? 1.55 and 1.3 microns. So here the V number would be 2.3. Right, so recall V number was inversely proportional to wavelength, right? So for 1.3 micron, the V number is higher than at 1.55. And now again, going back to the last class, remember we had empirical formulas for given a V number and fiber parameters like core size, we could find out the coupling coefficient as a function of the separation between the cores here, right? So, so if we use a separation D, which is about 13.8 micron. Okay, so that means this normalized this in D bar, which was D over A, recall. So this is about 2.47. Okay, so if you use this separation, then the coupling coefficient from that empirical formula that we discussed last time. So at wavelength 1.55 micron, that comes out to be 6.5 per centimeter. Okay, so recall we just needed the V number and this D bar to calculate this coupling coefficient. Okay, and then at the other wavelength, the coupling coefficient. So now at 1.3 micron, right, the mode will be more confined into the core, right? That also you can see from the V number, because the V number is higher, right? So that means the mode is more confined into the core, which means that the coupling coefficient will be actually smaller, right? For 1.3 compared to 1.55, because the mode doesn't leak out much to couple with the other core. So here the coupling coefficient is smaller. Right, so this is our okay, so now, so we've decided on some separation, right? Which gives us some coupling coefficient. So now we can decide on a length here such that these conditions are satisfied. Okay. So if we choose, for example, L of this 9.67 millimeter, so kappa 1 L comes out to be roughly 6.28 something. Okay, so it's close to 2 pi. Right, so this is 9.67 millimeter, and here, so in per millimeter, this is 0.65. So when you multiply this, you get something which is close to 2 pi, 6.36. And then kappa 2L comes out to be about 3 by 2 times pi. Okay, so you can see for m equal to 2, right, this condition is being satisfied. So basically, kappa 1L is 2 pi, and then kappa 2L is 2 minus half times pi. Okay, so for a coupler with these parameters, this much length and this much separation, right? So these are the design parameters. So while fabricating the coupler, these are the two things we want. Right, so for those parameters, we can have a coupler which will separate 1.55 and 1.3 micron wavelengths. Or equivalently, if we send 1.55 and 1.3 micron on the two separate ports, it will combine them into one port. Right, because this device is reciprocal. So if you reverse everything, right, so if you send lambda 1 from here, lambda 2 from here, then you get lambda 1, lambda 2 option. So basically what's happening is, if we plot the power coupled to the second port, right, as a ratio of the input power, sent in port 1. So for the two different wavelengths, right, so as a function of the coupler length, right, so if we look at 1.55 micron, so now this is a phase match case with identical fibers, right? So 100% power can actually be coupled. So actually, this is port 1. Right, so the power coming out from the same port as the input port. So for so it starts from 1, of course, for zero coupler length, right? So that means the fiber is coming straight. right? So every time this kappa L increases by pi by 2, the power is transferred to the other port, right? So when it first becomes pi by 2, then the entire power is transferred to port 2, right? And so it happens here. So this is for 1.55 micron, right? So or at L equal to pi over 2 kappa, the entire power comes out of port 2 and 0 power in port 1, right? And then if I increase another pi by 2, then power comes back to port 1, right? So now recall here kappa 1 L is 2 pi. So basically we get 4 times this power transfer, pi by 2, pi by 2, pi by 2, pi by 2. Okay, so at this length 9.67, which is somewhere here, right? So now the power has come back to port 1 for lambda 1. Right? So I hope that's here. So every time kappa L increases by pi by 2, the power is transferred to the other port. Okay. So 2 pi means there are 4 of them. So 1, 2, 3, 4. Right? And now for the other wavelength. So now the coupling coefficient is smaller, right? Which means so pi by 2, kappa L will reach pi by 2 at a longer length. Right? So this for the other wavelength it looks something like this. Okay, so this dotted line is for 1.3 micron. Right, so it has a longer oscillation period because it has smaller coupling coefficient, right? And so basically kappa 2L is 3 half of pi, so 3 times pi by 2. So you'll get 3 power transfers, right? So 1, 2, and then 3. So at this length of 9.67 millimeter, right? So for lambda 1, the entire power comes out of port 1, and for lambda 2, entire power comes out of port 2. Okay, so we've discussed this case for 2 specific wavelengths. Sometimes what you want is like you want a bandwidth, entire bandwidth of wavelengths around. So let's say not just lambda 1, but some range of wavelengths around lambda 1, and some range of wavelengths around lambda 2 should also have this functionality, right? Not just these 2 exact wavelengths. So for example, if I change lambda 1 to let's say 1.57 micron, it should still work. Or if I change lambda 2 to 1.32 micron, it should still work. Okay. So to make sort of these more broadband devices, typically what is done is we don't use identical fibers, right? Because for identical fibers, the sensitivity to wavelength is larger, right? So if you change wavelength, then the coupling coefficient changes by a larger amount. So if you want to make sort of more wavelength insensitive devices, then typically we go for dissimilar fibers with finite delta beta. Okay. So of course, then we can't get 100% power transfer, but we can. So we saw last time basically the relevant quantity is delta beta by 2 kappa, right? So with reasonable amounts of delta beta, so delta beta by 2 kappa less than 1, we can still transfer more than 50% of power, for example, right, and get this functionality. So, for example, and you can do even more fancy things, like for example, so recall how this was made was these fibers were sort of placed close together and then like heated up and melted and fused together, right? So while that process is being done, basically you can even tune sort of like you can pull one fiber change the core size or change the spacing here as a function of length also. Okay, so those would be tapered couplers where, for example, the distance between the cores is actually a function of propagation distance, or the core size of one of the fibers is also one propagation distance. So you can play these games and make the devices more wavelength insensitive or operate over a broader bandwidth. So now I mean you can get these WDM couplers operating over quite a wide bandwidth nowadays, like tens of nanometers around some specific wavelength. So for example, recall when we were discussing EDFAs, right? So we had a pump. So for EDFA we want, so there is a pump which is at 980 nanometer, right? And then there is a signal which could be anywhere in the range 1.53 let's say 1.57 micron, right? And these two signals are co-propagating in the fiber, and due to this strong pump at 980 nanometer, this signal is getting amplified, right? So of course, so this will be some different laser, right? And this would be some signal traveling through some fiber. So we need to combine them, right, into this erbium loop fiber. So how do we combine this signal? Is again using some WDM coupler like this. So we'll have some coupler here. Right, so here we'll send in the pump 980 nanometer, and here our signal is coming in at whatever wavelength. Right, and they both combine into this port 1 here, right, and nothing comes out of port 2. Right, so basically the kind of response you want. So I plot this insertion loss value that we discussed last time as a function of wavelength. Right, so if I look at the so the pump basically goes, input is port 1 and output is also port 1. So this is called the through port. Okay, so this 1 to 1 channel, this is called the through port. And the other one, so 1 to 2, when it couples to the other one, this is called the drop port. Right, so we can plot basically the power in the through port and the drop port as a function of wavelength. So the through port looks something like this. So the loss is very low at this 980 nanometer wavelength because we want that to go through. Okay. So put some numbers here. Okay, so this is for the through port. So the loss is minimum at around 980. Okay, so the wavelengths around 980 nanometer will go through without much loss, but any other wavelengths will have high loss for the 1 to 1. And if I plot the other drop port, so that the 1 to 2 path, so that has a minimum loss around these wavelengths. Okay, so the bandwidth here could be like 30-40 nanometers. So that, right, I can use the same coupler for different signal wavelengths that I want to amplify. So if you look at a spec sheet for a typical 980-1550 WDM coupler, right, that are used for EDFs, you would see a profile like this. Okay, so nowadays you can find these fiber couplers like both power couplers, splitters, and these wavelength division WDM couplers at various different wavelengths that you want depending on your application. Any questions on this? Otherwise, we finish our discussion on directional couplers and move on to the next topic, which is a different fiber optic device. What about the 2 to 1 ports? Yeah, so I mean, typically, as I said, the kappa 1 2 and kappa 2 1 are similar, right? So the response for 1 to 2 would be similar to the response for 2 to 1. But as I said, for these kind of couplers where you want some wavelength insensitivity and also the wavelengths are quite different, right? 980 and 1.55. Typically, these fiber 1 and 2 will be different, right? So they will be dissimilar. So in that case, kappa 1 2 and kappa 2 can be can have some significant difference. So in that case, yeah, so the 1 to 2 response won't be exactly the same as the 2 to 1 response. But so, for example, if you have a coupler which is working for closer range of wavelengths, so there are, for example, these CL band couplers or splitters. So C band wavelength is basically 1.53 to in this range, and then L band is like 1.57 to 1.6, right? So if you want to split and combine, so those wavelengths, so then the fibers will be basically similar. So in that case, the 1 to 2 and 2 to 1 both will have the same response. But typically, when the wavelengths are different, we have designated ports, right? So if you look at the actual device, they will mention that 980 should enter from this port, right? So if you send 980 from this port, the response, the performance will be worse because kappa 1 2 is not equal to kappa 2. So, when you get the coupler, they will mention that this port is for 980 and this port is for 980 because the fibers are dissimilar. Signal is an input to Yeah, sure. I guess I plotted the reverse, right? If I send from, if I send both pump and signal from here, then they come out here and here. That's what I plotted. But yeah, in the diagram, if the input is from here, then what you're seeing is right. This should be 2 to 1. Okay. So this plot I plotted if I send both pump and signal from port. So of course this would be the same, right? So so the response that so if you send input from 1, then the output you get at 2, right? So that response is the same as if I send from here and get the output here, because it's a reciprocal device. There is no direction. But the difference could be from if I send input from here and look at the output for on the drop port here, or if I send the input from here and look at the drop port here. Those could be different. Okay, so next topic of discussion is fiber polarization controllers. So we had briefly discussed about how polarization sort of evolves in single mode fibers, right? So there is, because of, we saw that non-uniformities and stresses, etc., the polarization is actually not maintained, right? And gets scrambled while propagating through the fiber. So for communications, for example, that leads to polarization mode dispersion, which needs to be compensated for. So there are devices called fiber polarization controllers, which you can actually use so inline to compensate for this, periodically compensate for this polarization scrambling. So whenever you have any fiber device, like let's say even if you're making some fiber laser or some fiber optic based device, and typically you want some particular polarization to be maintained, then you have to use these fiber polarization controllers, because the fiber itself, because it's cylindrically symmetric, it does not have a preferred direction, and because of stresses and non-uniformity, we saw that the polarization gets scrambled. So for many applications where we want a particular polarization to be maintained along the fiber, then we need these fiber polarization controllers. Right, so actually the idea is based on the same effect which causes the polarization scrambling. Okay, you can use the same effect to actually build a device by which you can actually control the polarization and make it back to what you want again. Okay, so basically the idea is that if you bend a fiber, right, that causes some stresses on the fiber because of the bend, right? So you can imagine, so if you are bending a fiber, the inner, so the fiber has some thickness, so the inner surface closer to the center of curvature, right, that is getting distorted less than the outer surface, right, which is further away from the fiber. So there are unequal compression and expansion, which leads to stresses on the fiber, right, and these stresses lead to birefringence, right. That is basically the two axes, the x and y, don't have the exact same effective indices anymore. Right. So basically, this was the effect that was causing this polarization scrambling and polarization mode dispersion. Right. So now for this device, basically we want to do this controllably. Right. So basically, so again, you imagine you have a fiber which you bend. Right. So there is some radius of curvature for this bend. Right. So if I now look at the cross section of the fiber, so typically the two axes orthogonal polarization for a perfect fiber with a perfectly circular core and no stresses, nothing, then these are degenerate, we know, right? But because of this bend, there is some stress caused in the silica material here, which changes the refractive index slightly, right? So, so if I call this the x, this is the y-axis. So the x-axis is basically in the plane of the bend, right? The x-axis is basically the axis in the plane of the bend, and then y-axis is perpendicular to the plane of the fiber or the bend. So what happens is, because of this stress, so the N effective, again, so recall we had these two modes, right? So let's say I have a single mode fiber, so the LP01 mode had these two polarization states, and for a perfect fiber, these two are degenerate. But now because of this stress, basically the N effective for this X polarized mode is no longer equal to the Y polarized mode. Okay. And actually what happens is that this x-axis becomes the fast axis, the in-plane axis becomes the fast axis, so the N effective the x direction is actually less, right? So the speed is higher, so that's why it's called the fast axis, and then the perpendicular axis is the slow axis. Okay. So there is a birefringence, right, which is the difference in the refractive index between the two orthogonal polarizations. Okay, so that depends on that can be empirically taken as a function of the bend radius, okay, like this. So you can see here, of course, it's inversely proportional to 1 over r square. So if I have a tighter bend, which means a smaller r, then the birefringence is higher, right? Because the stresses are higher. And so what is this B? So R is the radius of curvature of the bend. B is the outer radius of the fiber, right? This is basically the extent of the cladding. So far sort of we've sort of neglected the extent of the cladding, right? We just always take just the core size and then say it's cladding everywhere outside, but of course the fiber has some finite size, right? So you have some core, and then there's a cladding which we sort of assume it just extends till infinity, but actually it has a finite size, right? And why the approximation of this just extending to infinity works is that because the mode profile is basically 0 by the time you come here, right? So it doesn't matter what's happening here. But so this is a core size A, right? And then there is a cladding size B. Right, so typically for SMFs, as we saw, so this A is typically in the few micron range, right? So 3 to 6 micron typically, right? And this B is sort of a standard size. So this is 62.5 micron, right? So that the size of the fiber is sort of standardized, and no matter what fiber you have. So you could have different core sizes and different refractive index profiles here. This size, the actual bit fiber size is the same. So the diameter is 125 micron. Okay, so that's the standardized thing that people follow. So any type of fiber they make, the outer radius, the outer diameter, the size of the cladding is 125 micron. So this also helps, for example, when you splice fibers together if they are of the same size, etc. Anyway, yeah. So this B is typically 62.5 micron, which is the outer radius of the fiber. Right. So basically, this depends on the ratio of this size of the fiber to the bend radius, basically. And the C is a constant. Okay, so that just depends on the material parameters of silica, right? So depending on how much stress is applied, how much the refractive index changes. So this is some constant. So typically it's about 0.133, right? So this particular value is at visible wavelength of 630 nanometer. It's slightly higher at the near IR wavelengths, like 1.3 or 1.5 micron, but it's in this range, like 1.1 to 0.2. Okay, so we can estimate the birefringence that we get depending on the bend radius. Okay, so if we take a fiber and controllably bend it with a particular radius of curvature, right, we can induce a birefringence of a particular amount. Okay, so for example, if you have a bend radius of about 3 centimeter, right, this delta n, if you put the numbers here, right, this formula, these numbers basically, this value is about 10 to the minus 6 times 10 to the minus 7. Okay, so you can see it's a very small value, right? We discussed this also when we were discussing the polarization mode dispersion, right? These stresses cause like random non-uniformities along the fiber, and the level of those non-uniformities, the delta n's are around like 10 to the minus 7, 10 to the minus 6 range, right? Compared to the core cladding index difference, which is about 10 to the minus 3, recall. So these are very small, but they can actually be used quite effectively, as we'll see. So, so in the polarization mode dispersion case, we saw that this small value along a long length can lead to quite a bit of polarization scrambling. We can use the same effect, but controllably now to make these polarization controllers. So typically bend radius used are few centimeters or higher. Okay, so typically the lowest that we go is maybe couple of centimeters, not below that. Again, recall what happens when you bend the fiber is also there's a loss, right? Because we had a discussion on bending loss. So as soon as you bend the fiber, then actually the mode is the guided mode is not an eigen mode anymore, right? We saw that there is always some loss associated as soon as you have some bend, right? And that loss actually scales exponentially sort of with the bend radius. So typically for these fiber single mode fiber fibers, the bend radius, we saw that if the bend radius is beyond a few centimeters, then the bending loss is negligible. Okay, so typically we don't go below bending bending radius of 2-3 centimeters. That's the lowest that typically we go. Okay, so now let's take a fiber and let's bend it around into a radius. Let's say we have some spool of radius r, right? And we bend that fiber, we just wrap this fiber around that spool for n turns. Okay? So now in this region where it's coiling around n times, right? So let's say I send light here, which has polarization components in both the x and y, right? So this bending is occurring in a particular plane, right? This let's say the plane of the board, right? So we know what is the slow and the fast axis, right? So the polarization which is coming out of the board, that is the y-axis, that will be the slow axis, right? And the polarization in plane will be the fast axis. So for a given polarization with components in both these directions, we know that, or we can calculate that the phase shift between those two components right? So we know that there is a index difference created that will create a phase shift, right? Because so the phase is just beta times the length, right? Beta is the propagation constant, which is 2 pi over lambda times n effective. So the phase difference is basically the difference in the propagation constant, which is k naught times n effectives. So the difference in n effective will give me the difference in this delta beta times the propagation length. So the propagation length here is basically n times the circumference, right? And the circumference is 2 pi r, right? So that's the total length. So this is delta beta times L. So that's the phase difference between these two polarization components. And so we put this expression for delta n into that, so then we get okay. So here you can see that, so this basically, this spool of fiber here is acting like a wave plate, right? So in free space optics, basically what is a wave plate, right? A wave plate is a device which again has a slow and fast act, right? So it creates a phase difference between those two. Phase shift it adds. So for example, you have a quarter wave plate, which adds a phase shift of pi by 4 between the two orthogonal polarization, or you have a half wave plate which adds a phase of sorry, quarter wave plate adds a phase pi by 2, half wave plate adds a phase pi between the two orthogonal components, right? So basically this is something like that. It's like a fiber wave plate, right? So this is under our control, the number of turns, the radius of the spool, these are constants, and lambda is the wavelength of operation, right? So we can create a fiber-based wave plate, right? So if you choose the right parameters, so for example, if you choose the parameters such that this delta phi is equal to pi, then basically this is like a half wave plate. Right? And again, recall from a basic optics that half wave plate can be used to rotate the linear polarization, right? So the direction of the input light has some linear polarization along some direction. If you want to rotate that linear polarization along some other direction, you can use a half wave plate, right, placed at the right angle. So if this phase difference is pi by 2, then it acts as a quarter wave plate. Right, and quarter wave plates can be used, for example, to change linear polarization to circular polarization or back. Right, so basically, so for example, you choose the parameters, right, and then, so for example, you choose here n turns to get pi, right? Then you could have another section, let's say, which has n by 2 turns with the same parameters. So this will act as a half wave plate. This will act as a quarter wave plate. Okay. So again, we can look at some numbers here. So let's say wavelength is 630 nanometers. Let's say I have just a single turn. Okay. So then if I use a radius of curvature 2.1 centimeter, then I get a quarter wave plate. Right, basically the phase difference is 5 meters. Right, so now if I have 2 turns, then it will act as a half wave plate. Okay. And so what we can have is, so we can build a device which has this quarter and half wave plates in succession. Okay, and that can be used to compensate or recover the polarization to what you want. Okay, so again, from free space optics, it is known that let's say you have any arbitrary elliptical polarization, and you want to convert that into some other arbitrary polarization. Okay. So let's say, so at the input, you could have some arbitrary polarization you don't know. Right, so it could be linear or circular or elliptical in some direction. Okay. And you want to convert it to some other kind of polarization. Again, could be whatever, some elliptical, linear, circular, whatever. Okay, so you want to convert any arbitrary input polarization into any arbitrary output polarization. You can actually do that with a combination of 3 wave plates. Okay. So first, if you have a quarter wave plate, then half wave plate, and then another quarter wave plate, and then you can adjust the slow and fast axis. Okay, so the angle at which this is θ1, this is θ2, this is θ3. So you can play with the angle of the fast axis, for example, with the whatever x and y axis of the polarization directions that you defined. Okay, and so basically by adjusting these angles θ1, θ2, θ3 for these wave plates, you can basically convert any input polarization arbitrary into any arbitrary output polarization, right? So basically by adjusting these wave plates, you can compensate for any polarization, right? So polarization controller means you don't know. So at the input, some arbitrary polarization is coming in, you don't know. Okay, but let's say for your application, what you want is the output polarization should be linear, right? So basically, what you do with this device is basically you manually adjust these angles θ1, θ2, θ3 until the output polarization becomes linear. Okay, because so you don't know what the input polarization is. So you keep adjusting these angles and keep measuring the output polarization. And once you get the output polarization you want, then you set these angles to that. Right. So recall all these. So as the polarization is getting scrambled along the fiber, it's not at least it's a static distortion, which means that there is no time variation, right? So whatever scrambling is happening, the polarization here is fixed. It's not varying with time, right? So once you figure out what angles you need, then you can just set it. Okay. So of course, in a free space waveplate, we know that we can just manually, like it's mounted on some rotation stage, and we can rotate this angle. In a fiber, how do we do it? So basically, these fiber spools are placed on sort of rotation mounts. So the polarization controller looks sort of like this. So you have an input. So there's a fiber coming here. Okay. Input. Right, and then it's mounted like this. Okay, so you have a plastic spool kind of thing here. Okay, and so the fiber goes in here and it's like wound around into this spool here. Okay. And then you have another section like this. Right, and this is like a paddle that you can rotate in the so let's say this is placed in the plane of the board. You can rotate this paddle about the board axis. Okay, so you can like bend it out or in. Okay, so by that basically you are changing this angle. Right, so you're changing the orientation of the fiber axis. Right, so you're changing the plane of the bend with respect to the input x and y axis, right? You're changing the plane of that bend by bending this paddle. So that way you can control this angle. So basically you have three paddles like this for this on three wave plates, right? So this, for example, the other paddle is sort of more into the board. I don't know if you can make it out like this 3D. It's more exaggerated. Okay, so the fiber then comes here and then now it's wound around here. Right. So now this is bent more in. Right, so this will have, for example, n turns. This will have two n turns to make it lambda by 2. Right, and then you'll have another paddle here after that. So this will also have n turns. Right, and the typical size of these paddles again would be, so the radius would be a few centimeters. Right, and then the output comes out from here. Right, by adjusting these paddles, by setting them at some angles, you can change basically the polarization, let's say, from some arbitrary input polarization to what polarization you want by adjusting these paddles, which are equivalent to rotating in place. Okay, so basically you can use them in line, right? So the fiber is coming in, carrying the signal, then basically you can just connect them through some connector or even splice them in, right? And then the same fiber continues, but then you can control the polarization and then it continues. Right? So these are inline fiber polarization controllers. And so like you can get commercial polarization controllers which work over like this entire telecom range. With less than like 0.1 dB polarization So there will be some insertion loss for this device, of course. Okay. But for this polarization device, what is important is polarization dependent loss, PDL, which is the difference in the loss between the two orthogonal polarizations. Okay. So that difference is typically less than 0.1 dB, which means both polarizations have the same loss. Okay. So that means that, and the insertion loss typically is like 1 dB or less than 2 dB for this entire device. Okay, so these are very useful devices, fiber polarization controllers that are used in various applications. Yeah, so each section can rotate independently. So that, so I've shown here. So there is a straight section here in between the two, right? So the fiber is wound out, but then here there's a straight section here. So the fiber is going straight for some distance and then wound here. Okay. So when this is rotated, it has no effect on this one, right? So the fiber is, of course, there will be some twists like right at the sort of when it starts bending into the spool here, but that is sort of included in this bias fringes that we have calculated, right? And again, basically, this is sort of like basically, as I said, this is done manually, right? So you keep just adjusting the angles of these until you get the output polarization that you want, and then you keep it fixed. So if there are some stray effects like some twists happening slightly away from the spool, then basically you can take that into account while you're adjusting, and then but yeah, typically the spacing between these paddles are enough such that each paddle is independent and